As an example of calculating the mutual inductance between two circuits, let's just think about two ring-shaped wires. They are placed like that in such a way that their axis of symmetry are the same. They are coaxial, basically. Z is the distance between their centers, and I'm going to assume that this distance is much larger than their radii. So as a result, in that case, we can make some approximations in there. By using these approximations, we can compute the mutual inductance for that case. So the expression that we are going to write down will be valid in that limit. So I'm going to talk about this, of course. So in part B, I'm just going to describe what happens if the first wire is not a single wire, but it just contains some number of turns of wire. As a result, we will logically say that, of course, in that case, the mutual inductance would increase by that amount. But in any case, let's just go ahead with this. So how do I solve this problem? So basically, this is what I'm going to do. I'm going to assume that there is a current flowing on one circuit, and there is the second circuit in here. Right, that's the second circuit. We know that this current is going to produce a magnetic field, so that's what we call as B1. So we know that this magnetic field is very non-uniform. We couldn't calculate it, but at least we could calculate the magnetic field at all points on the axis exactly, so that was something exactly calculable. But of course, still, I mean, the second circuit is over a wide area, so therefore we don't know the value of the magnetic field at all points in there. So there are points in here whose magnetic field we cannot compute. We can only find the magnetic field at the center. Right? This is where the approximation enters into the picture. So this is the second circuit. So I need to express the second magnetic flux through the second circuit, assuming that there's current only in the first circuit. So that's basically B1 dotted with the area of the second circuit. So that's the expression. So what we are going to do is we are just going to approximate the magnetic field to be almost constant in there. So as a result, this is then approximately equal to B1 dotted with the area of the second circuit. All right, so let's just choose the directions like that. So I have chosen the direction in the counterclockwise direction when I'm looking from top on the first circuit. I'm going to do the same thing for the second one. So in that case, the area vector would be along this direction. So that's A2. Sorry, that's A2. Whatever. I'm going to write A2 in there. I don't have much space left. So you can see that the magnetic field and A2 are in the same direction. So therefore, the flux would be positive if the current is positive. So that's basically equal to B1 multiplied with A2. So therefore, this is like B1 times the area of the second circuit. All right. So there is a current I1 inside B1. So as a result, we have to express B1 as a function of I1. So that's the next step. We have already solved that problem before, but let's just solve it again. So let's say it like this. Find B1 in terms of A1. I1 in terms of I1. And in that case, the coefficient of proportionality would be R mutual inductance. So let's just do that. So this was a problem that we have solved by using Biot-Savart law. We are going to do the same thing again. So the picture is something like this. This is the distance C. I'm going to call that distance as R. This is little r1. So that distance is theta. So what we do in Biot-Savart law, we just take a length element in here on the side, and we say that this one produces a magnetic field in here, which is making this angle in here, which is dB1. What is that magnetic field? dB1. That's equal to mu0 I1 divided by 4 pi. And this is dl cross r unit vector divided by r squared. So r unit vector is that unit vector. In any case, we don't need that direction in here, because by using the right hand rule and the angles, we can express the direction like that. So as a result, the magnitude of that magnetic field is equal to dl divided by r squared in magnitude. All right, but we don't need this. We only need the z component of the magnetic field. So it's basically that component in here. So that's dBz. Let's write it down like that. Should I call this as dB1z? I don't know. That's the part that's actually important. So that's essentially dB1 multiplied with sine theta, where theta is that angle, which is the same as this angle. Right? This angle and that angle are the same. So as a result, B1z, which is essentially the magnitude of the total magnetic field in here, is the integral of this one. So that's mu0 I1 over 4 pi dl over r squared sine theta, that integral. And then we have said that somehow all of these quantities are constant, so I can take them out of the integral. And then what is left is essentially the circumference in here. So that's sine theta over r squared and the integral of dl. And then we have said that this is the circumference of 2 pi r1 of the circuit. Right, so therefore, we get like mu0 I1 over 2 r1 times sine theta divided by r squared. And that's essentially how we compute the magnetic field, total magnetic field produced by this wire at a point on its axis. This was the exact expression, but we don't need the exact expression in here. Exact expression is too complicated. So what we need is an approximate expression. So let's just remember this. Sine theta is exactly r1 divided by r. So that's approximately r1 divided by z. R is approximately equal to z. So therefore the magnetic field is equal to mu0 I1 divided by 2 r1 squared divided by z cube. All right, if you remember that last time we have derived this, we have said that I can multiply this with pi, and with pi there's an area in here. So area multiplied with current is the magnetic dipole moment, and so on. I'm not going to do that in here because I don't need, I just need the coefficient in here. So as a result, this is our expression for the magnetic field produced by the first current, the current in the first circuit at that location in here. So let's go back then for phi2 expression. So we have already computed this, so therefore this is equal to mu0 I1 divided by 2 r1 squared divided by z cube pi times r2 squared. It is strange that I get r1 squared from the magnetic field expression, and I get R2 squared from the area expression. That's actually very important. So therefore this is M21, multiplied with I1. So it's I1 multiplied with some number. So therefore M21 is equal to mu 0 pi divided by 2 R1 squared multiplied with R2 squared divided by Z cube. All right, that's the expression in here. Now we can discuss the physics in here. So let's see what the mutual inductance depends on. It depends on the distance between these circuits. And of course, it's inversely proportional to the cube of that distance. That means that if the circuits are far away, of course, the interaction is weaker. That's quite reasonable. The mutual inductance depends also on the area of the circuits. It's actually proportional to the area of both circuits actually. So it's therefore it's proportional to the product of the areas. You can think of it like that. That's also quite reasonable. And finally, there's the symmetry in here because somehow apart from the distance, the geometric shape only enters as area, at least for that special case. So that means this is symmetric. So therefore, if I computed M12, that's basically the flux produced by the second circuit on the first one. So basically there is a current in the second circuit and the flux is computed on the first one. We are going to get the same thing because of the symmetry in here. You can easily see that this is the case. So therefore, this is a situation where we can see that the mutual inductance is the same for either way. Finally, let's just compute an order of magnitude in here. Let me erase everything in there. So suppose that I have a circuit where, just for an example, I have a circuit where the radius is about 1 meters. And it's just there's a distance of 1 kilometer between them. It's just an example. I would like to see how the numbers come out. So if I produce some kind of a circuit in here, I don't know, a toy circuit perhaps, how would that affect the circuit of that size, which is 1 kilometer away? Will it influence much? So we can understand the number. So mu 0 is equal to 4 pi times 10 to the minus 7, but I forgot the units, but you can easily see that the unit is actually Henry per meter in here. So I'm going to write it down like that. But that's the numerical value. So therefore, M in that case would be, there will be 2 times pi squared times 10 to the minus 7. The squares of the fourth power of 1 would be in here. And then 1 kilometer is 10 to the 3 meters. So I'm going to take the cube of that. So pi squared is about 10. So that's going to give me 2 times. This is 10 to the minus 6 with 10 to the minus 9. So I get 10 to the minus 15 Henry. So that's the mutual inductance between these kind of two distant circuits. That's actually much smaller than what we expect. So typical values that you can meet in circuits, for example, is around 1 Henry. So as a result, you can see that this is extremely negligible. All right, so then let's pass to this last part in here. What happens if I have a coil with M1 turns of wire? So I'm going to do it like this. So I'm also going to add a page in here. So the first one, for example, is perhaps not a single loop, but there are many loops in here. So there are N1 turns. What does it change? You can actually think of it in many different ways. You can think of it as, if there's a current I1 inside the wire, there's a single wire in here with N1 turns, you can think of it as a single wire with one turn, but the current is N times I1, N1 times I1. You can think of it like that, which would then imply that so you're going to use the same mutual inductance expression, but this time the mutual inductance should be multiplied with N1 times I1 as the current to find the flux on the second one. And now if you would like to express this as a mutual inductance that multiplies with I1, in that case I'm just going to write it down like this. M prime 21 is equal to mu 0 pi over 2 R1 squared R2 squared times N1 divided by Z cube. So essentially the net effect is the multiplication of the mutual inductance by the number of turns. Okay, or you can think of it like this in the other way around. Let me erase this. So in that case, just look at the other way around. So there's a current in the second circuit that produces a magnetic field. So this thing doesn't change now. So there's a magnetic field B2 now. So that magnetic field passes from here. But the second circuit is a coil, and there are N1 turns of coil in here. You can then think of this as N1 many different circuits which are placed on top of each other. There are N1 loops. You can think of it like that. So instead of a single wire which goes around the same area many times, you can think of as N1 different circuits with each one has its own area. So as a result, the surface area enclosed would be multiplied with N1. So as a result, that would be equivalent to area being equal to N1 multiplied with the basic area of the coil. So that's pi times R1 squared. So that means when you're computing the flux, now the flux on the first circuit would be N1 times this area multiplied with B2. So you can also see that this expression also would be multiplied in the same way. So from here then you deduce that M prime 1 to basically the flux in the first circuit divided by the current in the second one would be just multiplied with N1. So therefore this is mu 0 pi over 2 R1 squared R2 squared over Z cubed times N1. You can also think of it like that. But in any case, you're going to get the same result because we know that these two mutual inductance values are the same with each other. And finally, it's just a final remark. If the second one is also a coil with N2 turns, in that case, of course, I have to multiply the mutual inductance with the number of turns of each circuit. So there will be N1, N2 multiplying factor in there. So this is actually a common theme. So if you have whatever the shape of the circuits are, if you have a coil with a number of turns, mutual inductance is proportional to the number of turns.